40 million lines of code.
Wow.
Yeah, that's Microsoft 365. Just let that sink in for a second.
That's huge.
It really hits home, doesn't it? The sheer scale of the software that, well, basically runs so much of our lives.
Mm-hmm.
And that's exactly what we're diving into today. You know, the fascinating world of how this incredibly complex stuff actually gets built.
Right.
We're going to unpack the processes, the methodologies, essentially the whole behind-the-scenes story.
Yeah, peel back the curtain a bit.
Think of it as finally getting a clear picture of that often invisible work behind the tech you use every single day.
Exactly. And we've pulled together some really insightful sources for this.
Oh, yeah.
We've got a great chapter on software development, really lays out the core ideas clearly.
Okay.
And then for that crucial historical view and, modern practices, we've got a couple of brilliant crash course computer science videos.
Crash course, always good.
Yeah, one on early programming takes you way back, and another one that dives right into modern software engineering.
Nice. So our mission today is pretty simple, really.
Mm.
Give you, our listener, a practical understanding of how software actually comes to be.
Right.
So whether you're prepping for a tech chat, just curious, or, love those aha moments with complex systems,
We got you covered.
we'll cut through the jargon, keep it engaging, promise. Okay, let's get into it. What's the first thing that jumps out from the sources?
Well, what's fascinating right off the bat is just how much things have changed, how much the field has matured.
How so?
The chapter points out that in the early days, software development was often like a really solitary thing.
Just one person coding away.
Pretty much. Programmers often worked in isolation. And this lack of communication, well, it led to wasted effort, duplicated work.
Okay, so people reinventing the wheel.
Exactly. And sometimes building solutions that weren't quite what was needed.
Right. You can picture it someone slaving away on code only to find out users needed something else or someone already solved it. Sounds super inefficient.
It really was. And that's where the realization must have hit, right?
Yeah.
That a more structured way was needed.
Makes sense.
Precisely. The source material really hammers this home. The shift to structured processes was driven by wanting better outcomes.
Like what kind of outcomes?
Well, things like actually meeting user needs consistently, staying within budget, which is always a big one,
Oh, yeah.
delivering on time, and, crucially for the long run, making the software easier to maintain and update later.
So fixing bugs or adding features down the road wouldn't be a nightmare.
Exactly. These are all fundamental goals that, good processes help achieve.
Okay, so from that need for structure, different approaches popped up. The chapter mentions two broad types, iterative and staged. Let's start with iterative. The big example they give is agile. You hear agile thrown around constantly in tech. What's the core idea?
The core idea of iterative, and agile specifically, is this fundamental concept of cycling back, reworking earlier steps when you find problems or get new insights.
So it's not just a straight line from start to finish.
Definitely not. It's deliberately not rigid or linear. The chapter highlights this idea of iteration going back, refining things. That's key.
Okay.
If you hit a snag or realize something's not quite right, Agile encourages you to revisit a previous stage and work through it again with that new knowledge.
Right, adapt as you go.
Exactly. The key insight with Agile is moving away from a totally fixed plan to something adaptive, something feedback-driven. It's about knowing requirements will change and having a way to handle that.
That makes a lot of sense. Like, okay, this isn't working, let's step back, fix it, then move forward, instead of just pushing ahead regardless.
Precisely.
And the chapter also mentions flexibility collaboration, especially that direct face-to-face chat with users.
Absolutely critical. That close, ongoing interaction with the actual users is central to Agile.
Why is that so important?
It gives you a much richer, more nuanced understanding of what they really need as the project goes on. Their needs might evolve.
Okay. So you can adjust course based on real feedback.
Exactly. It's all about open communication and being responsive.
So definitely not a fixed plan carved in stone, much more fluid. And the key features really show this. Frequent cooperation, responding to change even late in the game.
Early working software for feedback.
Right. Getting something usable out quickly, simplicity in design, self-organizing teams. Sounds pretty dynamic.
It is. Now, Agile still involves planning and documentation, don't get me wrong.
But flexibility is king.
Flexibility is definitely prioritized to get the best solution for the user. Now, on the other side, you have the staged approach. Example, waterfall.
Waterfall. Sounds more traditional, maybe more rigid.
It does feel that way. The name itself, waterfall, paints a picture, right?
Yeah.
Each stage flows down to the next.
Like water down a waterfall, you don't easily go back up.
Exactly. The chapter describes it as more formal, less adaptable than agile, a very linear progression through distinct phases.
And what are the key features there?
Well, formal documents are usually produced at the end of each stage, and those documents guide the next stage. Critically, a stage isn't supposed to start until the previous one is reviewed, signed off, totally complete.
Strict control at each step.
Very much so. The thinking behind Waterfall is that really thorough upfront planning and documentation is the best way to catch costly errors early.
Even if it means less flexibility later.
That's the trade-off, yeah.
And historically, the chapter says big companies liked Waterfall. Why was that?
The arguments were often around risk management and clarity. Spending a lot of time upfront defining everything was seen as minimizing expensive fixes later.
Makes sense for big, complex projects, maybe?
And all that documentation made it easier to track progress, especially for large teams where people might come and go. You could see clear deliverables at each stage.
So it's this fundamental trade-off, detailed upfront planning versus the flexibility to adapt.
Seriously.
Now, the chapter then brings in the software development lifecycle, the SDLC. It's presented as kind of a simplified model, mixing ideas from both.
Yeah, it breaks things down into key stages. It starts with investigate.
Right.
What's the main goal there?
The investigate stage is all about really understanding the problem the software needs to solve.
Okay, step one.
Yeah, the goal is to identify and analyze that problem and document it. This means figuring out, who the users are, what they need, what the client expects.
System capabilities, constraints like time and money.
Exactly. You need to deeply understand and define the problem first.
Can't build the right thing if you don't know what the problem is. Makes perfect sense.
Then still in investigate, you gather information. How's that done?
Well, you actively collect data. The chapter mentions things like interviewing potential users.
Get their direct input.
Right. Sending out questionnaires for broader feedback. Looking at any existing documents about current systems or processes.
Like a fact-finding mission.
Definitely. Build that complete picture.
Okay, facts gathered. Then comes the feasibility study. Sounds like a gonna-go point.
It absolutely is. It's basically a report for the client saying, okay, based on what we know, is a practical solution actually possible within the limits we have?
So it lays out options.
Yeah. Potential solutions with pros and cons, resource estimates, hardware, software, costs.
Timelines, training needs.
Benefits, drawbacks, even maintenance plans. Wow, that's thorough.
It really forces everyone to think, is this project actually viable before committing big resources?
Good point.
And the final step in investigate is specifying requirements, getting down to the nitty-gritty.
Exactly. What exactly is the software supposed to do from the user's view and the client's view?
So user requirements, what features they need. Client requirements, business value.
Yep. And also, hardware and software needs compatibility, storage, power. It also asks, could off-the-shelf software work?
Or do we need custom code? And if so, which programming language?
All decided here.
Okay, so investigate nails down the what and why. Next stage in the SDLC, plan. What's the objective here?
Plan is about figuring out the how and the when. The chapter stresses how vital a detailed plan is.
Why is that?
So everyone knows what tasks need doing, the timelines, and who's responsible.
Gotcha. Clarity for the team.
Yeah. It involves breaking the whole project into smaller tasks, setting realistic timescales, and identifying dependencies.
Dependencies, like you can't test code before it's written.
Exactly that kind of thing. Task A needs Task B to be finished first. The chapter mentions Gantt charts for visualizing this.
Ah, Gantt charts, those bar timelines showing tasks and links. Seen those.
Very useful. And planning isn't just tasks and time, right? You need people.
True. Staffing the project.
Exactly. How many people do we need? What specific skills should they have? That's all part of planning.
And I guess they use software for this now.
Oh, yeah. Project management software is very common for creating and tracking these plans.
All right, so we've investigated the problem, planned the attack. Now we hit design. This is where the blueprint comes together.
That's precisely it. Design is where you figure out the architecture, the structure, the components.
What kind of design approaches are there?
The chapter highlights a few. One key distinction is top-down versus modular design. How do those differ?
Okay, top-down starts with the whole system, like the big picture, then breaks it down hierarchically. Decomposition, they call it.
Right.
The example was a currency converter main system, then menu, calculations, input-output.
Got it. And modular.
Modular also divides the system, but into self-contained independent units called modules. Each does one specific task.
And these can be built separately.
Yeah, and potentially reused elsewhere. That's a big plus.
And the chapter stresses the benefits of modular, right? Code reuse, easier debugging because problems are isolated.
Makes the whole system easier to grasp, too.
Definitely.
Yeah.
What other design methods are mentioned?
Well, prototyping is big. Creating early, maybe basic versions to test concepts and get user feedback really early.
Smart. Test the waters.
Then there's flowcharting, using diagrams with standard symbols to show the logic flow. Though the chapter notes they can get messy for complex stuff.
Yeah, I can imagine.
And describing algorithms, listing out how functions will work using pseudocode, plain language, or flowcharts again.
And data. Huge part of software. How's that handled in design?
Crucial part, you create data and variable tables.
Okay, what do those track?
The data table lists all the data needed type, like text, number, date, storage needs, especially vital for databases.
And variables.
Variable table lists each variable name, its type, maybe its maximum length. The chapter also brings up key questions about data volume.
Like?
How many transactions? How much storage now and will it grow? How many people using it at once? Storage type, backups, privacy.
Wow, yeah, all incredibly important for performance and reliability later on.
Definitely. Now, a really central theme in modern development is keeping the user in mind. How does design address that?
User-centered design. It's highlighted as key prioritizing user needs at every stage.
Makes sense. Software's for people, mostly.
So making it effective, easy to use, is paramount. It means involving users in design, getting feedback, revisiting requirements.
And under that umbrella, they talk about UX and UD, user experience and universal design.
Yeah, could you break those down a bit?
Sure. UX, user experience, is broad. It's the user's whole perception, their feelings, preferences, before, during, after using the software.
Okay.
The UI, user interface, the buttons, menus, the visual layout is a part of the UX, a key part. The chapter clarifies. UX is the whole experience. UI is how it happens visually.
Got it. And universal design.
UD is about designing things so everyone can use them, regardless of age, size, ability. A big challenge because historically, software often aimed at an average user.
Who doesn't really exist perfectly for anyone.
Exactly.
And the chapter mentions tech to help with accessibility too.
Yes, adaptive and assistive tech. Adaptive is specifically for people with impairments like screen readers that read text aloud or special keyboards.
Okay.
Assistive tech is broader, might help disabled and non-disabled users like the Windows magnifier tool.
Useful for lots of people.
They also mention localization tailoring software for specific regions, languages, currencies, dates.
And internationalization.
That's designing it from the start to be globally accessible, adaptable to different languages, often using things like Unicode.
Thinking globally from day one.
And finally, designing for accessibility overall. It's a challenge, but often helps everyone, like video captions, helping both hearing and visually impaired users.
It's amazing how much goes into design beyond just the core function, usability, accessibility, the whole experience.
Totally. So after all that planning and design, we finally hit create. This is where the code gets written.
This is where the magic happens, yeah. Actually writing the code based on all that groundwork.
And if it's modular, different people can code different parts at the same time.
Exactly. Can speed things up a lot. The chapter also acknowledges reality. Sometimes you hit snags during coding that mean tweaking the design.
Iteration again?
Yep. Can be frustrating, cause delays, but that flexibility is often key to getting the right solution in the end.
And unit testing happens here too. Testing small code pieces.
Right. As developers write code, they test those individual bits to catch bugs early.
Smart. Fix them while they're small. Okay, code's mostly written. Now, the crucial, evaluate stage testing the whole system.
Absolutely critical. The chapter stresses it's not just does it work, but does it work correctly, consistently?
And does it do anything weird it shouldn't?
Exactly. And different tests happen at different times. Unit testing during create, then functional system acceptance testing after. And all this relies on test data.
Test data. Tell us more about that.
Test data are the specific inputs you feed the software to test it. They should be chosen carefully so you know what result to expect.
So you can check if the software gives the right answer.
Precisely. And you need a variety of data. Normal values within the expected range.
Incorrect values to test error handling.
Extreme values way outside the norm to test robustness.
And boundary values.
Right at the edges where behavior might change. The Leaving Cert points example testing right at the 80% or 89% mark shows why that's vital.
Yeah. Gotta check those edges. Okay, so you need diverse test data. What about the different types of testing in Evaluate?
Functional testing looks at each function or feature individually. Does it do what the spec says?
Checks usability, too.
Yeah.
Accessibility, error messages, security.
All of that. The process is create test data, figure out expected output, run the test, compare actual to expected, document everything. Can be manual or automated.
Okay. Then system testing.
That takes a broader view, tests the whole integrated system, does it meet all user requirements, do all the parts work together.
And that includes alpha and beta testing?
Yep. Alpha is usually internal testing by the dev team. Beta is releasing a near final version to real users out in the wild for feedback.
Get a wider range of eyes on it.
Exactly. The chapter also distinguishes white box and black box testing.
White box.
Tester can see the code, knows how it works internally.
A black box.
Tester has no code access. Tests it purely from a user's perspective, interacting only with the interface.
Like a real user would. Makes sense. And after all this testing...
A big overall evaluation. Does it work?
Yeah.
Meet requirements?
Yeah.
Is training adequate? Is it reliable? Cost versus budget? Lifespan? Value for money?
Wow, quite the checklist. Seems incredibly rigorous. Designed to catch everything possible before release.
That's the goal.
Yeah.
And the very final stage in the SDLC model. Document. Feels like an afterthought sometimes, but why is it so vital?
Documentation is absolutely crucial for long-term success, maintenance, understanding, even if it feels less exciting than coding.
What kind of documents are we talking about?
The chapter lists a ton: the initial feasibility study, requirement spec, design docs, the code itself with comments.
Test plans, test data, test results.
System documentation explaining the architecture, installation guides, training manuals, user guides, the final evaluation report. It's comprehensive.
Why is all that paper or digital paper so important?
It's essential for anyone needing to understand the system later. Developers fixing bugs or adding features, new team members.
Avoids knowledge getting lost when people leave.
Exactly. The chapter really slams undocumented code, says it hurts longevity. And good docs actually promote code reuse. Saves time later.
It really is the glue holding it all together, ensuring that knowledge persists. Now, the chapter also mentioned that development is usually a team effort. What roles are typical?
Definitely a team sport. Needs diverse skills. The chapter lists common roles. Business analyst.
They figure out user and business needs requirements.
Yep. Project manager oversees the team, tracks progress, talks to the client. System analyst designs the overall architecture.
Developers write the code, do unit tests.
Testers create test plans, run tests, document results. User liaison and training talks to users, creates manuals, does training.
And admin support handles logistics, scheduling, doc.
It's a whole crew all needing to work together.
Clearly a complex collaborative process today. But to really appreciate how we got here, it helps to look back, right, at the history of programming. That's where those crash course videos come in.
Yeah, the first one dives into early programming challenges. What was it like back then? So we've seen today's structures. Let's rewind and see how we got the basic tools like languages.
Well, that first video really highlights how different things were. It explains the shift from programming right at the hardware level
which sounds incredibly tedious and inflexible.
to more versatile software methods. Imagine physically rewiring a machine with patch cables just to run a different program.
Mind-boggling compared to typing code today.
Totally. The video uses the Jacquard loom from the 1800s as an early example, punched cards dictating the weave. Not a computer, but encoding instructions.
Then punched cards for the U.S. Census data.
But those early machines were hardwired for specific tasks. Not really programmable like we think of computers now.
And then came the plug boards and control panels. That video showed an insane tangle of wires for an accounting machine program.
Looked incredibly complex, took ages to set up, rewiring from scratch for every new program.
Just underscores the manual effort involved back then.
Absolutely. Even for ENIAC, the first general-purpose electronic computer, wiring up a new program could take weeks.
Weeks? That's crazy downtime given how expensive those machines were.
Exactly. It created this urgent need for a faster, more flexible way to program them.
And that led to the breakthrough, storing the program in the computer's memory.
Yes, along with the data. The video explains how electronic memory became practical in the late 40s, 50s. Paved the way for stored program computers, the von Neumann architecture.
Where instructions and data live in the same memory. A fundamental shift.
Totally revolutionary. Instead of rewiring, you just load the new program instructions into memory, often still using punch cards initially.
The video mentioned the Sage Air Defense System, 62,500 punched cards for its program. Imagine dropping that stack.
They even drew diagonal lines on the side striping just to keep them in order.
Wow, paints a vivid picture of the logistics. And other early methods. Punch tape, switches on the front panel.
Yeah, like the Altair 8800, literally toggling binary switches. Really shows how programming was for experts only, people who knew the hardware intimately. Difficult, error-prone, tedious.
And that difficulty drove the need for something simpler, more human-friendly.
Precisely. Which brings us to the next step, the rise of high-level programming languages. That's the focus of the second Crash Course video, moving away from low-level machine language.
Right. That video explains machine language. The raw binary zeros and ones is the only thing computers really understand. Early on, programmers wrote everything in binary or maybe pseudocode first, then painstakingly translated it by hand. Sounds awful.
Slow and full of errors. So the next step was assembly language, a small step up in abstraction.
Using short names mnemonics for instructions, like Lodo 14.
Exactly. But the CPU still doesn't get assembly text. You needed an assembler.
The assembler, a program itself written in machine code that translates assembly text into binary.
Spot on. A groundbreaking piece of software. Early assemblers got smarter too, handling things like memory addresses for jump instructions using labels. Made updates much easier.
But assembly is still pretty close to the metal, right? Still thinking about registers and memory?
Very much so. Still a one-to-one mapping mostly. You're still managing low-level details. Wasn't a huge leap in abstraction for the programmer.
And that's where truly high-level languages came in, the big step forward.
Yep. The video credits Dr. Grace Hopper as a pioneer here. Her work on the A0 language and the first compiler in 1952.
The compiler being key, one line of high-level code translates into many machine instructions.
Exactly. Much more human-friendly, much more efficient for complex tasks.
And there was skepticism at first. People thought computers could only do math.
Hard to believe now, but yes, Hopper proved them wrong. The video uses Python as a modern example. Adding two numbers is simple. No worrying about registers.
Introduces variables, too, using meaningful names for data.
A huge conceptual leap.
Then, 1957, Fortran arrives. First widely adopted high-level language.
Right. Formula translation aimed at scientists, engineers needing math formulas. The director even joked he'd do it because he was lazy and hated assembly.
Laziness driving innovation. And it made a big difference.
Huge. Fortran code was way shorter, easier to write than assembly.
Even with performance concerns initially.
The time saved for programmers made it economically sound. Then COBOL in '59, a business language aiming for write once, run anywhere.
Yeah, a consortium effort, though each machine still needed its own COBOL compiler.
True, but the source code could theoretically be portable.
And the biggest impact of these early languages.
Lowering the barrier to entry. Computing wasn't just for specialists anymore. Scientists, engineers, business folks could use it. A fundamental shift to a general-purpose tool.
And then came the golden era of language design.
60s to now. LGOL, Lisp, BASIC, Pascal, C, C++, AutoWL, Python, Java, Swift, C#. Tons emerged, many still used today. It's this ongoing evolution.
Always adding new abstractions, making things easier.
It really is remarkable. Which leads us right into modern software engineering practices, the topic of that second Crash Course video. Managing today's massive complexity, like that 40 million line Office suite.
How do they do it? The video stresses tools, processes, best practices. That's software engineering. Starts with breaking down big programs.
Into smaller functions or procedures, makes code easier to grasp, maintain, and lets teams work in parallel. We touched on that with modular design earlier.
But modern engineering goes further than just functions. Object-oriented programming, OOP.
Right. A powerful way to manage even greater complexity. What's the core idea?
OOP bundles data attributes and the functions that work on that data methods together into units called objects.
Okay.
The video used a car analogy, a cruise control object inside an engine object inside a car object. Hierarchical.
Objects containing other objects plus data and functions.
Exactly. And you interact via defined interfaces, navigating the hierarchy. It's another level of abstraction, hiding the low-level details inside these objects.
Hiding complexity by encapsulating details.
Yeah.
And inheritance, where new objects get properties from existing ones.
Yeah, promotes code reuse, makes the whole system easier to manage.
And this object structure is great for teams working together.
Absolutely. Breaking it down into these units is ideal for parallel work, like crews on a skyscraper. But for that to work smoothly,
you need good documentation and clear APIs, application programming interfaces.
Right. Explain the role of APIs.
An API is like a contract, a set of rules saying how different software components, maybe built by different teams, talk to each other.
Okay.
The video's ignition control example showed public functions like setting engine RPM, which cruise control needs access to.
And private functions like actually firing spark plugs, which only the ignition object itself should do.
Exactly. OOP languages let you specify public or private. This hiding complexity while revealing specific interfaces is central to OOP's power.
Allows teams to work independently without breaking each other's stuff. Crucial.
Totally. Beyond OOP, what other essential tools and practices are there?
IDEs, integrated development environments. Special apps that bundle tools programmers need.
Like what?
Fancy text editors with syntax highlighting, error checking, project organization tools, compiling and running code easily, and powerful debuggers.
Debuggers to find and fix bugs.
Yeah, and the video points out programmers spend a lot of time debugging, and maybe even most of their time.
Ouch. Highlights the need for good tools.
Yeah.
And documentation. We mentioned it earlier, but the video stresses it too.
Absolutely vital. Both separate README files and comments inside the code. Explains what it does, how it works, how to use it.
Makes sense for collaboration and maintenance.
Trying to work with undocumented code is a nightmare. Good docs also help reuse code later. Saves time.
Definitely. And with multiple people changing the same code, how do you avoid chaos?
Source control, or version control. Essential for teams.
How does that work?
Usually uses centralized servers, code repositories, storing the project's code history, like Git. Developers check out code to work on locally, make changes, test them, then commit them back to the central repository.
What are the benefits?
Prevents conflicts, lets many people work at once, keeps a full history, lets you roll back to old versions if bugs appear, tracks who changed what. Indispensable for large teams.
Makes sense. Finally, the video mentions quality assurance, QA testing. How's that different from earlier testing?
QA is often more formal, rigorous, maybe by a dedicated, independent team.
Their job is just to find bugs.
Find unforeseen conditions, edge cases, subtle bugs before release. Ensure high quality, good user experience. They also mention alpha testing.
Early internal tests, often buggy software.
And beta testing, releasing a near-final version to the public for real-world feedback.
Get lots of different users trying it out.
So, wow, we've really traced quite a journey today.
From isolated early programming to this highly structured, collaborative, sophisticated world of modern software engineering.
It really has been fascinating, and understanding these processes, even just at this level, I think gives you, our listener, a much deeper appreciation for the sheer complexity and effort behind the digital world we use every day.
Absolutely. Which, raises a really interesting question to leave our listeners with.
Oh.
Given this constant rapid evolution we've talked about, from hardware tinkering to abstract languages to complex engineering methods, what might the next fundamental shift be in how we create software?
Good question.
Will AI start writing more of the code directly? Or will completely new paradigms, new ways of thinking about development emerge that we can't even imagine right now?
That's definitely something to chew on. A fascinating prospect indeed.